Hey guys, so this is Unit 7, Video 3 on torque and rotational equilibrium, okay? So today we're going to talk about something we call torque as an angular equivalent to force, meaning that it's like force but in circles. Solve for problems in which torque causes rotational acceleration, and we're going to distinguish between examples of equilibrium, rotational equilibrium in structures, okay? All right. So we'll kind of go over these examples, and we'll talk about this kind of thing that Archimedes said back in BC. He said, basically, give me a place to stand and I will move the world. He was referring to the picture above, which is this one, which uses a long lever to move a huge mass. So there are lots of examples of torque, but essentially he's saying if I had a long enough lever, I would be able to lift the Earth or any large mass that I want to. So essentially torque is something that depends on the length of this lever and uses forces to sort of lift or rotate things. These are all examples of torque being used, and we're actually going to talk about all these in class so you can get more of a conceptual understanding. This lecture will go through mostly the mathematical understanding of torque, okay? So torque is the angular equivalent for force, meaning, like, remember how we have velocity and then we have angular velocity, and we have acceleration and then we have angular acceleration. So this is like the angular version of torque, so things that are rotating. So the way that a force makes something accelerate linearly, torque makes things accelerate in circles, okay, or rotate. So torque causes angular acceleration around a pivot point. All right, the equation for torque, we use this thing tau. It's like a fancy T, okay? Don't just write capital T because that's tension. So it's a fancy T, and it's force times, we're going to call it R, okay? And I'll explain what that is, times sine theta. All right, the units are, well, newtons for force. R is a distance, so it's in meters. And sine theta has no unit. Okay, so it's in Newton meters. All right, so here's a quick example. Find the torque produced by a 300 Newton force applied at an angle of 60 degrees to a door that is 1 meter wide. So R is the distance from the rotational pivot point. So if we have a door, right, and let's think about like the handles here, okay? This axis right here is the pivot, right? The door rotates around that point. So R actually really stands for radius, but it's the distance from the pivot point to the force, okay? So it's this distance. So we assume the handle is going to be out here. So this is where our force would be pushed, right? And our R is the distance from the pivot point to that edge. So since the door is 1 meter wide, we can expect that the R would be 1 meter, okay? But I'm going to write this over here. R is the distance from the force to the pivot point. Okay, that's very, very important that you have the correct R. All right, so we're going to go ahead and plug in. And you'll see that the torque is 260 Newton meters. Okay. Now there are two ways to increase torque. If you look at the equation, you can increase the force, okay, or you can increase the distance from the pivot point. R is the distance from the force to the pivot point. So you can increase the distance of the force to the pivot point. Those are the two ways. So going back here, the pivot point, if you were lifting this, you can imagine this would rotate sort of like up like this. That's the pivot point right there, right? Or actually, you could say here too. Either way, but it's somewhere on this side, right? So the longer this rod is, or this lever is, the more torque he's going to be able to exert, meaning the more chance he's going to have of accelerating that mass in the direction that he wants, okay? All right, rotational equilibrium. This is like an equivalent of net force being 0, Okay, so rotational equilibrium occurs when there are multiple torques acting on an object. So you need multiple forces, multiple torques, acting on an object to keep it from having any angular acceleration. So that in this case, alpha is 0. Okay, meaning that there is no acceleration, meaning the thing is not, sorry, I'll use this. It's not rotating. It's not rotating. Maybe I should go this way. It's not rotating. Okay, it's just sitting still. All right. This is exactly like free body diagrams we made for force, but now we define clockwise and counterclockwise direction. Okay. So we're going to always say, this is just write this over here, clockwise. Actually, we don't even need to do that. We don't even need to assign this. We're just going to leave it alone. Okay, so we're actually going to set up an equation that all the torques working clockwise equal all the torques working counterclockwise when we have rotational equilibrium. Meaning that all the things trying to rotate this are canceling out and the thing is not rotating. Okay? That's what we're saying. Here are some steps for solving torque problems. First, you're going to want to draw a picture. I'm going to obviously do this when I do the example so you'll see. You're going to choose a pivot point. This is key. You have to choose a pivot point. Okay, otherwise you're not going to know what R is because it's the distance from the force to the pivot point. If you don't know what the pivot point is, how can you decide what the distance is? Okay, you're going to choose a pivot point and you're going to choose a pivot point. And you're going to use your brain to choose which pivot point would be best. Okay, you'll start to get the idea. Identify which forces push clockwise or counterclockwise. You're going to set up this equation. This is the equilibrium equation, and then you're going to solve. All right, so here's an example. Just easier if I show you examples, I think. So as kids, Mr. Battle and Mr. Passion used to play on the seesaw at Cuesta Park, as shown below. If little Battle has a mass of 30 kilograms, so let's say mass of Battle is 30, okay, and he sits 3 meters from the center. So here's the seesaw, okay, and let's say this is Mr. Battle over here, okay, and his weight is what's pushing down on that seesaw, right? So his weight is the force mg, so 30 times 9.8. Okay, that's the force pushing down. He is 3 meters from the center, the fulcrum, or let's say the pivot point. Okay, we're going to identify that as the pivot point. Where would little Passion be with a mass of 50 kilograms? Where would he have to sit to make this work? Because if Mr. Passion sits on one end 3 meters away and Mr. Battle sits on one end 3 meters away, then they're going to just end up like this, and that's not fun. So we need it to sort of be balanced. That's the goal. We want it balanced. So where would he have to sit in order to make this work? We're trying to find R for Mr. Passion. Okay? We know his mass is 50, so his weight would be 50 times 9.8. The reason we're finding weight is because these are the forces that they're exerting on the seesaw. Okay? And this is the pivot point. So we've chosen a pivot point, we've drawn a picture, we're going to identify which forces push clockwise and which ones push counterclockwise. Here's how I do this, and you guys need to follow this, okay, because otherwise it gets very confusing. Use your pencil, okay? Pretend that your fingers are the pivot point. So put it on the pencil where the pivot point is. So in this picture, it's in the middle. So I'm going to choose the middle. Okay. Then you're going to pretend that you're each force. So first I'm Mr. Passion. He's sitting over here somewhere. Okay. And I'm going to push down as if I'm exerting force like Mr. Passion. Which way does the pencil rotate? For Mr. Passion, it's rotating clockwise. Okay. So the torque caused by Passion is clockwise. Okay? Now, the torque caused by Mr. Battle is over here. If his force is the only force, it rotates counterclockwise. Okay? So the torque caused by Battle is counterclockwise. All right? Now we're going to set up the equation. So the torques clockwise equal all the torques counterclockwise. There are no other forces on this seesaw. Okay, clockwise is Passion, so we have torque caused by passion equal to the torque caused by battle. Okay, and then we have to plug in Fr sine theta for each torque. So for passion, we have F, which is 50 times 9.8. That's the force. His R is unknown. And because he's pushing down, the angle is between the force and the moment arm, or the lever, or the seesaw. So that angle is 90 degrees. Okay, so sine of 90 is 1, so we don't even need to write it. But let's do it anyway, just so that we're clear here. Okay. Battle, his force is 30 times 9.8. His R is 3, pivot point to the force. He is the force to the pivot point, 3. Sine, also 90, because his force makes a 90-degree angle with the seesaw. Okay? Now you can plug this into your calculator. All right, and you end up getting like 490 R equals 882, and R ends up being 1.8 meters. Now, it would make sense that passion would have to sit closer to the pivot point and have a smaller R than battle because he exerts a bigger force. So if we want their torques to be equal, the one with the bigger force is going to have a smaller R in order to make it equal to the guy with a smaller force and a bigger R. Okay? So that answer does make sense. All right? Let's do a few more. Something to note really quickly before we continue. And actually, I'm going to have you cross this example out. It's actually a double. It's down here. It just got typed twice. I'm not sure why. Okay, so just get rid of that. Something we need to talk about before we continue with torque is that center of gravity plays a role. Okay, so every object has a center of gravity, and the center of gravity is the point where if I were to hold it, like if I were to put pressure at that point, so like with the pencil, that's where it's balanced, right? If I were to put my finger down here, it falls, or over here, it falls. But if I find the center of gravity, oops, then I can get it to balance, right, without falling. Okay, so the center of gravity of this pencil is like right about in the middle. Okay, the reason we need to know the center of gravity is because if the weight of the object is causing a torque, we need to be able to mark where that force would be. So for a sphere or a ball or like an evenly spread out mass, so like a baseball or a soccer ball or whatever, center of gravity is going to be in the middle. Okay. For a hammer, well, these are a lot heavier at the top. So the center of gravity is closer to the top, somewhere around there. Okay. For a sword, it's usually heavier right where you're holding it. So maybe center of gravity would be somewhere around there. I'll show you why this is important, but most of the time, the center of gravity is in the center unless they tell you otherwise. So you can assume the center of gravity is in the middle unless they tell you otherwise. Okay? All right, let's do a few more. These are essentially the same steps that I showed you before. Okay, I just put them over here so you have them as a reminder. Okay, so let's do this example. Okay. A 12 kilogram sine, that's this sine, it's hard to read, but it's 12 kilograms. We're going to assume that the weight of the sine comes from the center of the gravity of the sine. Okay, so the center of the sine. So the force would be 12 times 9.8. Okay, that's the force caused by the weight of the sine. It's held at the end of a 10-meter pole. So from here to here, from the length of this pole is 10 meters. Okay, I'm just going to note that up here so it's not in the way. The pole has a mass of 50. So the pole has a mass of 50. They didn't tell us that it was not in the middle, so we're going to assume that the weight of the pole is in the center. The center of gravity is in the middle. So I'm going to put the force of gravity from the pole in the middle. Okay. If the sine is 2 meters wide, so from here to here is 2 meters, Okay? How much tension is in the rope before it breaks? So this rope is what's holding everything up. Okay? Now, if the rope were to break, you have to think about how would this thing rotate, right? So if it were to break, here's the pole. If this rope were to break, this would rotate down, right? It would rotate down. So the pivot point is what it's rotating around. So hopefully you can see that if it were breaking, it's rotating around where my fingers are here at this corner. So the pivot point, the smart pivot point to choose would be here. Okay? Okay, now let's decide. We found the pivot point. We found the center of gravity of the objects. Now let's go ahead and figure out which of these forces, 1, 2, 3, are clockwise and which ones are counterclockwise. So we'll just make little lists. Okay, so here's how you do it. Remember this. You hold on to the pencil, okay, at the pivot point, and then one force at a time, you use the other finger to pretend that you're that force. So if I'm this force, I'm pushing from here, and the pencil rotates clockwise. So this one, that force is clockwise. Okay, I'm actually just going to call it the torque of the pole. Okay. Okay, next one for the sine. It's pushing down here, rotates clockwise. So the torque of the sine is also clockwise. Okay. Last one, the tension, is pushing up counterclockwise. So the torque caused by the tension is counterclockwise. Okay. That's how you figure those out. Now, we set up the equation. Torque clockwise equals torque counterclockwise. The torque of the pole. Now remember, it's not just the force of the pole. It's the torque of the pole. So the torque of the pole is 50 times 9.8, that's the force, times R. Remember, R is the distance from the force, so here, to the pivot point. That distance, since this is in the center of the pole and this pole is 10, is 5. Okay? This is at 90 degrees with the pole, so we don't have to worry, sine 90 is 1. Plus, okay, so that's the torque of the pole. Torque of the sine is also clockwise. So we have the force of the sine, 12 times 9.8, times the distance, R, from the force to the pivot point. Okay, this is a little more difficult. Since this is 2 meters wide, and this is in the middle of that sine, there must be 1 meter from here to the end, right? 1 meter from here to the end, which means if the whole thing is 10 and that's 1, then this is 9 from here to the pivot point. Okay, so that's 9. Also sine 90, so 90 degrees. Okay. Equals, that's all the clockwise torques, equals the torque caused by the tension. Well, the force caused by the tension, we're just going to call it tension. We don't know what it is. The R is the distance from the force to the pivot point. Force to the pivot point. If that's 2 and the whole thing's 10, then this must be 8. Also 90 degrees, so we don't have to worry about the sine 90. Okay? Let's plug that into our calculator. Okay, so this side is 1058.4 plus 2450 equals t times 8. And if you solve for t, you get 439 newtons. Okay, so that's the tension in the rope that it can withstand without breaking. Okay. All right, let's do one more, just to get you guys used to it. And we're going to practice a lot in class, but try and follow the steps here. Okay, 2 people are holding up the ends. This one's kind of hard, okay? There's 2 forces. 2 people are holding up the ends of a 4.25 kilogram wooden board. Okay, so if the mass of the board is 4.25 and they didn't tell us that the center of gravity is anywhere but the middle, then I'm going to assume that the weight of the board is going to come from the center. Okay, so this is the weight of the board, and it's equal to 4.25 times 9.8. Okay. The board is 1.75 meters long. We can see that here. Okay. A 6 kilogram box, that's this box, sits on the board. So the weight of that box would be 6 times 9.8. And it would pull down. Okay. And it sits 0.5 meters from the end, as shown. Okay. So I actually probably should have drawn this a little bit further over on that line here. Okay. And then you have two people holding it up. So they're putting forces on the ends to hold it up. Right? You can imagine their hands underneath pulling up. So I'm going to call this force 1 and this force 2. Okay. Now, this is really tricky because you're going to have to solve these two forces separately. All right. So the trick is you're going to have two unknown variables. The trick is any force that is exerted on the pivot point. Okay. So had we had a force on the pivot point, it would have no torque. And the reason for that is going back to your equation, is that if r is 0, the distance from the pivot point to the force, if that's 0, there's no torque. Okay? So if you push on the pivot point, it will not rotate. So the trick is, in order to not have two variables, is to make one side the pivot point. Okay, so pick the pivot point to be at force 2 there. And we're going to solve the problem there. So I'm going to say part 1, pivot point at force 2. Okay? And then I'm going to set up my equation. Torque clockwise equals torque counterclockwise. And let's decide now. So pivot point's here. Okay, we have two forces down, so you can't really see. There we go. We have the weight of the board clockwise. Okay, so torque of the board plus the weight of the box, also clockwise. Okay, and then the force of F1 counterclockwise. Okay. Torque of the board is going to be the force of the board, so 4.25 times 9.8 times R. R is going to be half of the length of the board. So 1.75 divided by 2 is 0.875. Oops. Okay, sine 90, okay, they're all 90 degrees, plus the weight of the box times R of the box, so this is, be careful, the distance from this force to the pivot is 1.25, equals the torque of force 1, so force 1 is the force. R is the whole length of the board. From that force to the pivot point is the whole length, so that's 1.75. Okay? And if you solve this for F1, you get 63 newtons. Okay? That's force 1. Now, in order to solve for force 2, we're going to change the pivot point. So in part 2, we're going to make the pivot point over here. Okay? So now part 2, pivot point at F1. We would do the exact same thing. Okay? So torques clockwise equal torques counterclockwise. Now the pivot point's over here, so I got to refigure out what they're doing. So these downward forces, counterclockwise. Other one, counterclockwise. So the torque of the board and the torque of the box are both counterclockwise. And the torque of this F2 is clockwise. Okay, set it up. So this is going to be F2 times R, which is distance from here to pivot point, which is the whole length. Torque of the board, 4.25 times 9.8. Still half of the board length, so it's still 0.875. Okay, now here's where it's different. You still have the weight of the box, 6 times 9.8, but the r is different now. It's not 1.25 because the pivot point moved. So now from here to the pivot point is only 0.5. Okay, so now if you solve this equation for F2, you get 38 newtons. That's the force 2. Okay, so that's as pretty much as hard as it can get, all right, having two parts like that and having to move the pivot point. So I wanted to give you an example of that. At some point we will see a tension that's at an angle. Okay, I'll do that during the warm-up so you have a chance to see that. And then we will also talk about all these conceptual questions here, these little ideas here, that just to make sure you got the concepts down. But math-wise, try and really go through this and make sure you understand, and then we're going to do some examples in class because these are tough. Okay?